We're gonna look into theory of system design. So the idea of this lecture is to introduce you to some of the different type of requirements and how to formulate them for your system. So this is coming from two different sources. This is not part of your textbook material. I'm using two references here: engineering design of systems and model-based systems engineering. Both textbooks are listed as part of the references in the syllabus.
This one. Canvas.
Yeah, it should be Canvas for today. So the agenda for today, we're going to look into these 7 items. We're going to start looking at system design versus systems analysis. And then how do we go from stakeholder needs to stakeholder requirements? And then we're going to look into the different type of requirements, starting with the system design requirements, the functional system design, buildable system design, and the type of requirements that are needed for you to transition from a functional system design to a buildable system design, and the type of requirements that are needed for you to transition from a buildable system design to an implementable system design. And then finally, last part of this lecture is discussing the system test requirements. So what are the differences between system design and systems analysis? We, as systems engineer, we need to make sure that it's our responsibility to ensure that the system satisfy all the requirements through the life cycle. Okay, so those requirements that we are going to postulate for our system, we need to make sure that those are connected to the customer. And at the same time, once those are defined, we need to find a way to make sure that those are requirements that are satisfied. System design is first piece here is where we design a system, is to develop a model on the basis of which a real system can be built, developed, or deployed. And that model will allow us to see whether or not we can satisfy all the requirements. System design is creative, right? So there will be things that are new that you have not seen, probably like a new component or maybe a integration of pieces that is new. So this is usually applied to a system to be created, one that has not existed before, or that is developed to replace an existing system. The concept of systems analysis is similar to that of system design. From the system analysis perspective, we want to look into a system or analyze a system is to develop a model by means of which a real system will be managed, controlled, augmented, evaluated, or modified in order to satisfy all its requirements. So you build a model, you can use that model to make sure that the requirements can be satisfied. And then you can also use that model to perform different experiments to analyze what will be the performance and if something needs to be adapted in order for you to satisfy the requirements that are postulated. So both of them, system design and system analysis, depend on models. The concept of system analysis is usually applied to a system that already exists. And what we're trying to do is to improve that performance. System analysis is sometimes applied also to a system that is presumed to exist, but is actually represented only by a model or a computer simulation, where we are trying to evaluate the performance of such concept. Okay, so that's the first item, looking at the differences, where you see both of them requires models. You're going to be using them for two different perspectives: designing, making sure that the concept that we are proposing is satisfying the requirements that are postulated. If you're doing analysis, whether or not the changes that we make to maybe our requirements are not necessarily accomplished at this point. So we are making these changes. We are also using the model to analyze if those changes are going to help. So one of the things that we've been doing so far in this class is to define the problem, understand the needs analysis. That was a lecture that we did last time. So now we want to go from those needs, the needs of the stakeholders, to define some requirements from our system. So here's our different flowcharts. Actually, it's just one flowchart that we're gonna try to go step by step here in this process, in which we're trying to establish this system or these stakeholder requirements. So several steps are necessary to understand the maturity of the stakeholder needs and to understand how to improve upon that maturity. Okay, so if you see this, we start here from the top left side. We are studying the context. What are the real needs? And we go from there, right? We start here at this top left part of the diagram. And as we move forward, we are trying to be more specific about what are the things that the system must do and what are the requirements that we need to satisfy. So we start with the real needs, those that lie behind any perceived needs. So as you can see here, this highlighted top left part. So for example, a generic need could be the ability to identify infectious diseases easily. So a need that was present a few years ago here in the United States and in the world. Often real needs appear to be simple tasks, right? So in this example, we are just saying, oh, there's a virus. We need to find ways to identify these viruses so we can make decisions. Okay, if you are sick, please stay away and do not exchange those viruses with these people that are still healthy. So that could be a generic need. However, that's not necessarily what we need as we move forward with our solution, right? So perceived needs are based on the person's awareness that something is wrong, that something is lacking, that improvement could be made, or that there are business, investment, or market opportunities that are being capitalized upon. Perceived needs are often presented as a list of organized expectations resulting from an analysis of the uses conditions from the considered action. So for example, the real need might be perceived as a need to carry out medical tests in particular circumstances. Those could be laboratories, point of care, hospitals, and or human dispensaries. So instead of identifying, now we're going to be more specific, right? We need to carry out this test in order to identify whether or not this person is sick. Since the real need is seldom clearly expressed, richness of the knowledge of the perceived needs is used as a basis for potential solutions. This step has to be as complete as possible to cover all the context of use. So we are moving now to the next part, right? We're still looking at the needs. What's the needs? What's the problem, right? How do we address that problem? So we move from perceive, right? This is the awareness of something needs to help. I mean, I need something to help me with this problem. So for example, if we move to the express needs, these originate from the perceived needs in the form of generic actions or constraints and are typically prioritized. So for example, if safety is the primary concern, the express needs to protect the operator against contamination may take priority over those express needs such as assist in the execution of tests. So now it's not only performing the test, but also those people that are going to be performing the test, is those are primary concern because we want to make sure that we keep them healthy. Then we need to protect them, right? So that could be a primary concern. When determining the express need, the analysis of the expected mission or services in terms of operational scenarios take place. So, okay, we found the problem. Now we try to be more specific in terms of, okay, the problem is not necessarily that we have these viruses, that we don't have ways to identify the virus itself. So that's the perceived need. And now we go into more detail in terms of what's more important. We need to make sure that we not only care about the public, but also the people that are going to be interacting with them, doctors, nurses, and so on. So after that, we have perceived needs, expressed needs. So we need to make a selection, right? And that's what we call the retained needs. These are selected from the expressed needs. The selection process uses the prioritization of expressed need to achieve a solution or to make attainable solutions feasible. Exploration of potential solution must start from this step. And the various solutions suggested at this step are not yet products, but describe means of satisfying these stakeholder requirements. So those needs that we are going to keep, that we're going to retain based on that list of the list that we have created from these express needs, those are the ones that are going to be leading to defining the stakeholders' requirements. And also to start visualizing potential solutions. Okay, so from the retained needs, we establish our stakeholder requirements. Potential feasible solutions might be also visualized at this point. But from there, we can also move into the specified needs, are the translation of the stakeholder needs to represent the views of the supplier, keeping in mind the potential, preferred, and feasible solutions. These are the needs that we are using to translate into what the system has to do, the system requirements. Right, so from retained needs, we define our stakeholder requirements. These are the things that we need to make sure we satisfy for our customer, but we can go deeper in terms of, okay, so we know we need to accomplish those requirements, but how is that translated into my system? And next, after design and implementation, we move into realized needs. Are the product, service, or enterprise realized, taking into account every specified need, and hence the retained needs? So that will lead into the product that we are going to develop. Okay, so I believe this is very straightforward, right? But this gives you an idea of the processes that are happening in terms of beginning to develop your requirements for your system. So let's start with what we call system design requirements. So system requirements, these are developed to address the need and objectives of the stakeholders. The stakeholders, basically your client. Requirements are a specification. And there's going to be a hierarchy associated with the requirements, just as there is a hierarchy associated with the system. So we have the customer requirements in this pyramid, which is typically at the top. We have the mission or the needs requirements. And from there, we have the originating requirements that those are coming from the customer. And then using that information, we want to specify the detailed requirements, such as the system requirements, subsystem requirements, component requirements, configuration, and so on. So we start with the mission or the needs requirements. These are related to the needs associated with the mission or activities that are important to one or more groups of stakeholders. They might be related to the system of system level in the hierarchy, and they represent the stakeholders' preferences for increased ability to perform their activities with the introduction of maybe a new system at a lower cost and faster time. The originating requirement, these are the statements by the stakeholders about the system capabilities that define the constraints and performance parameters within which the system is to be designed. We, as systems engineer, we take this and we go deeper in terms of the level and derive detailed requirements. And we will refer to these two categories of requirements as the customer requirements. The customer will include all the stakeholders and any interested parties or those that will be affected by the system to be developed. And then we move into the detailed requirements. Will include the system requirements, subsystem requirements as stated already. And these have to be documented, and every major organization has established its own guidelines. So depending on where you end up working, if you end up working as a systems engineer, you will have different guidelines in terms of how the company would like you to set up your requirements. So as we move forward, we as systems engineer will start restating the customer requirements and deriving requirements in engineering terms. These are called system design requirements or simply system requirements. So at this point, we want to address the what and the how. Well, the system must perform certain functions. And remember that requirements are a specification and thus not provide any solutions at this point. So in this class, we are going to consider these 6 categories of requirements. First, the input-output requirements, technology requirements, performance requirements, cost requirements, trade-off requirements, and then system test requirements. These are the 6 different types of requirements that we are going to study. So the statement of a system design problem consists of explicit definition of these 6 requirements, and then collectively, these requirements are called the system design requirements. And mathematically, we can express them like this. So the system design requirements are a set of these 6 different types. And this is a very difficult problem to solve. So we'll start with the input-output. That's number 1. And this is typically the first step for any system. We need to define the inputs that the existing system shall accept, process, or receive, and the output that the system shall produce. So at this point, the specifications are in terms of the length of the operational life of the system to be designed. So for example, the length of the operations phase of the system life cycle, the set of inputs to be accepted by the system to be designed, and the set of input trajectories or histories with it might be a mic experience. So if you're familiar with simulation, typically what you have is just a model that is reacting to certain inputs, like a video game, right? So if you're playing a video game, there has to be some input from the user in order for the software that runs the game to react. That's what we call the input trajectories, right? If you select a sequence of buttons that you are pressing, you know the software is going to be executing something, and that based on that, there's going to be an output. So when we are designing a system and we want to test it under certain conditions, we basically build a model, and then we also need to build this input trajectory that we're going to feed into the model to see how is it going to react. Like if you, for example, if you're looking at an airport checkpoint and you're building a model to represent the operations of that checkpoint, there's a set of input or input trajectories that could be based on the arrivals of the passengers. So you might have group of 5, group of 10, group of 1 arriving at certain points in time. So you can build that input trajectory as a set. At time 0, I'm going to have 100 people showing up. At time 1, I'm going to have 20 people showing up. At time 10, I'm going to have 200 people showing up. And I want to run my model based on that input trajectory and see how it's going to react. It's going to react differently if you only have 1 person showing up every 5 minutes, that if you only have, or if you have 100 people showing up every 10 minutes. You know that the system is going to be operating differently and the output is going to be different. So that's what we are trying to define now. We not only want to know what the set of input to be accepted, what are typical input trajectories that are observed for your system. If the university were a computer model, you know the input trajectories during the fall semester are going to be different than during the summer, right? In which you don't have as many students on campus. So those are the type of scenarios and input trajectories that we want to create. And the set of outputs will be produced by the system to be designed. And we also need to know, okay, if I'm counting people that are going through the security point every hour, or among keeping track of the time in the system, how long does it take for a person to go from entering and leaving the system? So those are the type of output trajectories that you have to decide what's important for your system and how are you going to be selecting those. The eligibility function that matches outputs and inputs, or input trajectories and eligible output trajectories. That's what we call an eligibility function. And it limits or specify the behavior of the system to be designed, and is usually based on physical law. So if you think about machine learning, that's typically what it does as well, right? You have a set of inputs and a set of outputs, and you're trying to match that history of going from input to output using different type of algorithms. And that's basically what we are trying to do with this eligibility function. How do you connect this input trajectory to this output trajectory in a model itself? Typically, this also could be based on physical laws, depending on the system that you're observing. So every system interest to systems engineer accept and process inputs and produces outputs. We call the output system concept and the dynamic system model. Input examples could be inputs to a computer. So at any given time, the input from the computer will be considered the collective conditions of all the input ports at that instant of time. So it could be not only the keyboard, or you might be using the keyboard and the mouse, or you might be also sending a signal for printing. So it's not just the keyboard, the mouse. You might have a different type of inputs happening at the same time, and your design has to accommodate those. And then that's part of the challenge. How do you decide what goes first? How do you prioritize, and so on? Output examples include the image on monitor, information on the hard drive, signals to the modem, printer, etc. Any given time, the output from the computer will be considered the collective conditions of all outputs ports and that instant of time. If we kept a record over a period of time of all the output from a computer, that record will be an output trajectory, and we are going to define it as OTZ. Okay, so that's system design requirements. We are moving forward. Now we want to start looking at the functional system design. The input-output requirements determines a set of system designs that satisfy the input-output requirements. A functional system design, or FSD, is a system design that satisfies the input-output requirements. Okay, so for example, if you know your input is saying you're gonna get 10 passengers every 5 minutes, your output is saying you had to process every passenger should take at most 10 minutes to go through their checkpoint, right? So you have people arriving every 5 minutes, 10 people arriving every 5 minutes, and you want to make sure that your system is able to produce or to get them out of the system in less than 10 minutes. So how do you match this with this? Any system that logically is able to take that input and transform it into this output is what we're going to call a functional or function system design. Right now, we are not thinking about technology. This is more like, okay, these are the functions, right? And logically, I can come up with a way of saying, if I have a server that do this and this, and take into account these pieces in the process, I should, and each piece of the process take about this time. Yeah, I should be able to generate a system, a system that can be built in reality. But if the input trajectory is saying you are going to get 1 million people every 5 minutes, and you need to have them out of the system in less than 10 minutes, you know that in reality, you might not be able, unless you have like a very, very big facility with many, many staff members, which might not be practical, right? So that's the type of analysis that we are trying to make. So an FSD specify what the system should do in order to accomplish its mission, and can be thought as a logical design that satisfy the input-output requirements, specify what the system should do, and now not how the system can do what it should do based on the available technology. Some functional system design may not be buildable in technology. So for example, an FSD could be defined to specify instantaneous mass transfer, a function not implementable in any technology known at the present outside of science fiction. So again, getting into that level of not real, right? We know that that's not buildable in technology, so it might not be functional in terms of your design. Okay, so from that, we move into technology requirements. So one important thing, remember this. This could be a question in your exam. FSD is a system design that satisfies the input-output requirements. Okay, so we cover input-output. If you can come up with a design that satisfies these input-output requirements, that's what we call a function system design. Now, moving forward, technology requirements for a system to be designed consists of the set of components that could be hardware, software, human, bioware, considered by the designers and the customer to be available to build the system. The technology for a system to be designed is frequently referred to as the available technology. And how the system can be built is determined by the existing technology. Okay, so first we focus on what the system is going to do logically. With the technology, we try to satisfy that logic or those functions and see if there's any technology that we can use to make that happen. So we went from functional system design to buildable system design. And this one, we are trying to address the how the system can be built to perform as specified by this functional system design. A buildable system design is a design specifying the system that results from coupling together components, all of which are in technology. A buildable system design may not satisfy the input-output requirement. Okay, so that could be one of those systems that are not gonna work, right? Who has not built a system that does not work? That's the question. So buildable system design is a design specifying the system that results from coupling together components, all of which are in the technology. So basically, you're taking the technology requirements, and if we can satisfy those technology requirements, then we're gonna have a buildable system design, something that we can build.
Wait, I'm confused on that one.
Yes. So we went from input-output and defining logically a system that can satisfy the inputs and the outputs, which is functional system design. So it's in terms of functions. Now we're specifying technology requirements, and here is where we are trying to address what technology can be used to satisfy those functions that are from the functional system design. If you can specify using available technology, how the system can be built, then you're satisfying those technology requirements.
What would be an example of that?
So going back to the example of the airport, right? So you have, from a functional perspective, you have these many passengers arriving per time period, and you have to get them checked in less than 10 minutes, right? You don't want them to wait more than 10 minutes. That will be the functional design. So in between, you have certain things that needs to happen. One function is to check the passenger so he's not carrying any items that could be dangerous. Another function would be to check the luggage, right? To make sure that they're not carrying any dangerous thing in their luggage. The other thing could be if they're carrying liquids, making sure that the liquids are not dangerous, right? So you have all those pieces. Now, when you're looking at the technology, how are you going to check for the luggage? How are you going to check for the passengers? What type of technology can you use to make those functions for your system happen? How are you going to check for the liquids that they're carrying? You need to have some type of test to use to make sure that if they carry, let's say, a bottle with some liquid and they're meeting the standards, sometimes they have just to check if there's not a chemical substance that is dangerous. They have like a test. So that's the technology. That's what you're trying to define here in this technology requirement. But let's say that you define as a function that passengers might need to be checked in groups of 10 at the same time. We might not have a technology right now in which you can check 10 people together at the same time, right? So that might not be applicable in technology. So that's the type of thing that you're trying to say at this level. I have a way to build this functional design with this existing technology. And that's what the technology requirement. And if that's the case, if you can satisfy those requirements, then you can state that you have a buildable system design, because your functional system design can be implemented with the technology that you have already specified.
So what does it say it may not satisfy?
Oh, so a buildable systems design may not satisfy the input-output requirement. So let's say that you are pushing to the limit, right, in your system, saying like you want to take it from waiting 10 minutes in the process to 5 minutes, right? And then you stated that as your functional system design, and then you move forward with the technology that is already in place, and then you end up noticing that the technology that you refer as potential technology that can get you to that point is not gonna take you to that point. It's not possible. So you have a buildable system design that is not working because it's not letting you achieve that goal that you have established for your functional design. So in that case, you might need to come up with maybe new technology. And that's where we get to the risk assessment, right? Are you gonna propose something new that have not been tested before as a potential piece of your system? A technology that might need to be developed, tested, and so on. So I don't know if that clarifies what you're trying to say. So that you come up with a functional system design that when you try to implement some technology, maybe the technology that you selected is not gonna allow you to get to that performance that you were looking for. So that's what I mean by building a system that does not work for the goals that you have stated. Okay. Good question. Okay. Performance requirements. They specify how well the input-output requirements shall be met. Okay, so we use some performance figures of merit, like for example, the response time, capacity to response, expected quality. So if you look at the card, that could be things like how long does it take you to go from 0 to 60? that will be acceleration. The maximum speed, maximum horsepower, or minimum horsepower, torque handling, those can be easily specified in terms of performance. Performance requirement for a system to be designed is an algorithm by means of which any two functional system design can be compared consistently with respect to how well it satisfies the input-output requirements and is defined in terms of performance figures of merit and their thresholds. So what we want to do with these performance requirements is to have a way to compare, right? So when we start looking at different options, I don't know if you, I mean, again, I'm like cars. So you look at this car magazine, sometimes they compare different models and they have these plots in which they show, okay, in this, or tables in which in this range or in this performance, this guy did better. In this performance, this guy did better. That's the trade-off, right? So if you're making the decision about which car to buy, you have to look into this different performance. And then according to what's best or better suit for your needs, you can make a decision in terms of which one will be a better option. So that's the idea with these performance requirements. You're comparing any two functional system designs with respect to how well is satisfied the input-output requirements. So a performance figure of merit is a function defined over the space of the functional system design. For every functional system design, it must be possible to compute or estimate the value of performance figure of merit. Ultimately, the performance requirement is stated so comprehensively that any two functional system designs can be compared with respect to how well each satisfies the input-output requirements, where how well is defined in terms of performance figures of merit. And then we have also performance thresholds for each real value performance figure of merit. An upper threshold and a lower threshold are defined. So for example, in the case of a design of a car, the lower and upper threshold for fuel consumption might be 30 miles per gallon and 40 miles per gallon. A functional system design that has a value for a figure of merit smaller than the lower threshold for the figure of merit is either impossible or unacceptable. Similarly, a system design that has a value for a figure of merit larger than the upper threshold for the figure of merit is impossible or unacceptable or based on our requirements. Okay, so now we get into the finances, cost requirements. This is based on what the system will cost to build and operate in terms of cost figures of merit. So that could go from the capital required, expected operations and maintenance costs, the life cycle costs, environmental and social costs, and the trade-offs among these cost figures. So performance, we're looking at the functional system design. For the cost requirements, we are looking at the build system design, buildable system design. It must be possible to compute or to estimate the value of such cost of figure of merit. So if we have an idea of the technology that we want to use, we can start estimating this cost. Ultimately, the cost requirement is stated comprehensively that any two buildable system designs can be compared with respect to how much it will cost to build and operate in all the dimensions in which this cost must be represented. The cost requirement for a system to be designed consists of an algorithm by means of which any two buildable system designs can be compared. So for the performance figures of merit, we can compare two functional system designs and find out which one will be performing better according to our goals. When looking at costs, now we are comparing the buildable system designs, because those are the ones that have technology associated with them, and that could be used to compute the cost. Cost of figure of merit is a function defined over the space of the buildable system design. And again, we will have some thresholds for each cost So if you go above or below those thresholds, then you are not going to take that concept into account. Okay, so the last one is the implementable system design. We say that a buildable system design implements a functional system design when the buildable system design has a mode of behavior that exhibit the same functional capability or functionality as the behavior specified by the functional system design. Each of the system functions specified by the functional system design is assigned for execution by one or more of the components or subsystems specified in the buildable system design. Every system exhibits several modes of behavior. For example, failure mode, operational mode. In addition to these, a computer exhibits modes of on, off, internal checking mode, and so on. An implementable system design, or ISD, consists of a functional system design together with a buildable system design that implements or realizes the functional system design. Okay, so this is the third one. You already have a functional system design. You have a buildable system design. So if this buildable system design satisfies the functions that were stated in the functional system design, then you say that you have something that you can implement. When a functional system design is realizable by a buildable system design, the pair of design constitute an implementable system design. The functional system design part of the ISD specify what the system is supposed to do in order to satisfy the system requirements, and the buildable system design part specify how it is to be built. So here's an example or an illustration, right? So what we have here is, go from the left, we start with our functional system design, right? So this is stated, is only one, right? These are the functions that the system must perform in terms of input outputs, and how are you going to connect those inputs to the outputs, right? So we have this functional system design. And from there, using different technology, we can come up with different options for buildable system designs. So for example, if you use technology A, that could be buildable system design A. You use technology B, you have another potential concept, which is a buildable system design B. And if you use other technology, you have a third option. From there, if this can be taken into an implementable system design, so let's say we are looking at different components. The first one is saying that they are going to be using, let's say, Windows technology. So from here, this design is implementing this. So based on that, it meets the functional system design. So I have an implementable system design 1. System 2, or buildable system design B, is meeting the functional system design as well. So I have an implementable system design 2. Let's say this is a Mac. And then I use a third technology, let's say Linux technology, but that technology is not meeting my functional system design. So this is not an option. It's not an implementable system design. So out of this analysis, you start with this input-output functional system design. You look at different technology options, and then based on that, you check whether that technology can implement this design. If the answer is yes, then you have an implementable system design. If the answer is no, then you are no longer considering that design. That makes sense? So this kind of put together all this discussion. Okay, so our goal, first step, is to come up with input outputs and find a logical way of satisfying the outputs based on the inputs. Then if that's the case, we want to check if there's technology available that can help us build such a system. If the answer is yes, then we might end up with different options. Now the challenge is to check whether that technology is going to be able to execute the FSD. If the answer is yes, then we have an implementable system design. If the answer is no, then it's no longer an option. And then let's say you have two options and you want to pick one. That's the next step. For that, we need what's called a trade-off requirement. And this is an algorithm by means of which any two ISD or implementable system designs can be compared consistently with respect to trade-off between the performance and cost requirements. The trade-off algorithm can only decide the preference between two ISDs. So you can only compare two at a time, choose one, and then bring the third one, compare those, bring the fourth one, and then so on. But it's a comparison among two. When they are equivalent with respect to both performance and cost, when the comparison with respect to performance does not agree with the comparison with respect to cost. Two ISDs can be compared both with respect to performance and cost. Performance because each ISD includes a functional system design, and cost because each implementable system design includes a buildable system design. A trade-off figure of merit is a function defined over the set of implementable system designs. The trade-off requirement is usually defined in terms of performance, cost, and trade-off figure of merit and their thresholds. So here's an example. Suppose that you have to decide between two system designs, S1 and S2, based on expected revenue and expected cost from each system. Let the expected revenue for S1 and S2 be denoted as R of S1 and R of S2 respectively, and the corresponding expected cost being C of S1 and C of S2. How can we compare these two system designs, S1 and S2, in terms of both revenue and cost? Well, we can start with the revenue, and we can have some logical statements like this one. So if the revenue of S1 is greater or equal to the revenue of S2, and the cost of S1 is less than or equal to the cost of S2, then S1 is at least as good as S2. If R1 is greater to S2 and CS1 is less than CS2, then clearly S1 is preferred to S2. If you have a combination of factors, then you might need to provide some additional logical statements to differentiate between them. What if RS1 is greater or equal to RS2 and CS1 is greater or equal to CS2? Then comparing S1 and S2 is not trivial based on these four. In this case, we can compute the expected profit and use it as a basis for comparison, right? So now we're looking at the difference and then we're comparing the profit. Another way to perform a comparison is to perform a benefit cost analysis. So how many of you have taken engineering economy? So that's, I believe, is something that you should have seen in engineering economy, how to perform a benefit cost analysis. So you compute that benefit cost ratio, the ratio of the expected benefit to the expected cost, and this often referred to as the bang for the buck. And then you use those ratios to perform the same logical comparison. Last thing is the system test requirements. The system test situation by comparing candidate implementable system designs with respect to performance, cost, and trade-off requirements, and implementable system design is chosen, and on the basis of the ISD, a real system is built. The real system must be tested within the context determined by the system requirements and the implementable system design. An implementable test requirement is a pair consistent of an implementable system design and a real system built on the basis of that implementable system design. So STR, or system test requirements, specify for each possible implementable test item observance, conformance, compliance, and acceptance. So we have 4 areas that we need to check of whether or not this real system is doing what it's supposed to do. So observance, you observe, sample, measure, simulate, and so forth in order to estimate a value for each performance cost and trade-off figure of merit. The set of estimates of the values of all these figures of merit is called the test data. Conformance. How should it be proved in terms of test data that the real system is conformance with the implementable system design from which it was built? Compliance. How shall it be proved in terms of test data that the real system is compliant with the system requirements? And acceptance. How shall it be proved in terms of test data that the real system is acceptable to the customer? So again, from 4 different perspectives, we have to check if this implementable and real system is addressing what it was designed for. So here's a illustration, trying to put together all this into a single slide. So we went through describing what is a functional system design and a buildable system design, how both of them are needed to come up with an implementable system design. Using that design, we come up with a real system. And then using our test requirements, we check for observance, conformance, compliance, and acceptance. And that if we are able to satisfy all those areas, then we're done with our system design and implementation. And that's it. Questions?